You may have very confused perspectives on what gravity really is, and it's really hard to find a good description because people always like to ask questions that just can't be answered. But today, I will give you a lesson on what it truly is, and what makes it such a mystery even though it's pretty much here all the time in our daily lives. Some of you actually may find this a lot more interesting than it sounds. I will go around the basics of the main phenomena, which is the basics of gravitation. Gravitational attraction is a really strange and remarkable force which little can be known about. It's kind of hard to experiment with gravitational force because the masses in a laboratory are just way too small. You know, the force needed to test these things are on planetary scales, which would be impossible to examine or even test. For instance, it's easy to switch on and off electricity, but there's no gravity switch, which is a shame. But we're living on a perfect example of gravitation, which, of course, is Earth and the Moon. For instance, how does the Earth pull the Moon, even though it's 400,000 kilometers away from Earth with a vacuum between them both? Newton was to calculate that the Moon travels at 2.6 times 10 to the power of minus 3 meters per second. He used different units, but
this is the way.
He compared the acceleration of the Moon with the acceleration of objects falling on Earth. In modern units, this is a table of the obtained numbers. It's about to get heavy with numbers. Gonna use the acceleration of an apple as a cheap joke here, but this is the equation needed in order to find the ratio of the values, followed by this equation. So let's just break this work down. So the Moon is 60.1 times further away from the center of Earth, but the acceleration is merely 1/3610th of the apple's acceleration. Now these numbers may seem very different, but notice how 60.1 times itself equals 3610. There it is. Newton's inverse square law of gravitation, proving that every particle of matter in the universe attracts every other particle with a gravitational force, directly proportional to the total masses of those particles, which will be perfectly inversely proportional to the square distance between them. Here's the equation form of what I just explained if maths is your forte. So F is the gravitational force, has the same magnitude on each particle, which are m1 and m2, and they are the masses of the two particles, and r is the distance between them. G is the gravitational constant, which is found experimentally. Now it may seem like the mind-blowing thing is that he solved the fact that maths can be used to connect the acceleration of the Moon and an apple, but it's the fact he has now discovered that the motion and force affecting the apple is the same motion and force affecting the Moon. This proves that gravitation is a universal force. I'll put it in simpler terms for people who might think I'm just rambling. Gravity occurs because an object has mass, and it's a daily occurrence in our lives, walking, eating, blood flow, even architecture, to a point where it's even in our vocabulary. We say picking up the kids from school, or dropping down to the shops, yet these things that it does are completely peculiarities. Gravity keeps the air that we breathe in contact with the ground. Without gravity, the air would just drift away into space. And it even makes the very existence of Earth possible, because without it, we would have never formed from the countless bits of rock and dust 4.6 billion years ago, and the Sun would have never formed without gravity. It makes it possible to have communication with satellites, talk to our friends, watch TV. It even keeps you healthy. You would lose all muscle and bone mass. You can go as far as to call it magical. Anyways, gravitational attraction. It's like if one magnet moves past another, then there is an appreciable attraction or repulsion between them, and if you walk past a house, you feel no attraction or repulsion at all. Yet there is an attraction. There is always an attraction and never a repulsion. The reason that you do not notice the attraction is that the force is so very finite for a house of mass of 200,000 kilos and a person mass of 60, and the force of attraction if the person's 10 meters from the house is only 0.000008 newtons. This is a force which is practically impossible to notice, but it was the basis of the first attempt to measure gravitational force in 1740. And it was always known a large gravitational force will only exist if at least one of the masses is large. Larger the mass, larger the gravitational force. Usually the force of attraction between two masses which are not spheres can be very, very, very difficult to calculate. This is because gravitational forces exerted on or by any sort of a typical sphere, a uniform sphere, is the same as if the entire mass of the sphere were just put right in the center. Now, just before I get onto gravitational fields, I will say if you would like a part 2 of something like this, please do comment and mention it, and I will continue. Anyways, gravitational field strength at a point is defined as the gravitational force per unit mass acting at that point. You can sort of imagine that very complicated description as the way a magnetic field surrounds a magnet when it's been drawn out. The same type of diagram can be drawn to show the gravitational field around really any body. Well, this type of body. You can see how there is a difference between the magnetic field and the gravitational field because, magnets have attraction and repulsion. Gravitation is always an attractive force, so the gravitational diagram will only show attraction. And weirdly enough, because this drawing is supposed to be of a perfect sphere, this diagram is technically 3D. Little backtrack to Newton's second law, we know that F equals m times a. We can pretty much say, just using this equation, that the units of gravitational field strength will be exactly those of the acceleration. So, the gravitational field strength at Earth's surface has a value of 9.8 newtons per kilogram. This, by default, pretty much tells you the acceleration, which of course is due to gravity, and that gives you 9.8 meters per second. So once you actually start to leave the planet, so from the surface of the Earth upwards, the value of the strength of the gravitational field on Earth will decrease following an inverse square law. This is a very commonly seen graph for people who are highly interested in physics. Anyways, within the Earth, this value follows a very confusing and complicated variation because the density of Earth is never constant. It has a core, it has a crust, outer crust, these all have different densities from one another, of course the core being the most dense. And using measurements or examples taken from the speeds with which shockwaves from earthquakes travel, it is actually possible to calculate these values in all kinds of distances and places from the center of the Earth, and this is how the graph is made. So, the reason it's actually drawn in this way is just to show that the gravitational field strength at the center of the Earth is 0, because any matter at the center will be pulled equally in all directions, giving a resultant force of 0. The second reason is the graph actually shows the direction of the field is in opposite directions on opposite sides of the Earth. So on the diagram, the field on the right hand side acts towards the left. This obviously shows that it has a negative value. The field on the left hand side acts towards the right and is shown as the positive side. All of this complicated maths clearly shows that trying to find the field for even so much as just two bodies in space, of course we're doing the Earth and the Moon, it's a very, very lengthy process. But the pattern produced by this process is much as would be expected, which is, of course, perfect. If you were to ever see any pictures of the gravitational field of the Earth-Moon system, you will very clearly see that the Earth's field dominates this region of space, with the Moon's field having an influence only comparatively close to itself. We're not including the field of the Sun because it's 99.9% of the mass of the solar system. We wouldn't even see the mark that Earth has made. And because there are objects in motion in a gravitational field, this makes it a vector quantity, which is very difficult to make calculations of speed and energy of the objects moving in this field. So whenever a field theory is used, it is therefore useful to define a scalar property of the field at each point, and this property is called the potential of the field. And, like we've been saying, in this case we define the gravitational potential of a point in the field as the work done on unit mass is moving in to the point from a point remote of all other masses. So, in a very simplified term, the gravitational potential of a point is equal to the potential energy that a unit mass would have at that point. So, in just the way that a force can be calculated from the gradient of potential energy, a field can be calculated from the gradient of potential. To go on about this, it would take me hours. So I'm going to have to cut this very short here, but if you would like me to continue this, maybe do a recap of a previous topic I've talked about, please do tell me and do comment, and please do like and subscribe. Every little helps, and thank you so much for watching.